Let's see how well this works. I think this will work. Alright, I'm going to be continuing to design the software for my motor controller. You can see my board over here. It's connected to this linear actuator, and there is a servo here. Right now it's running DC motors, but this board is designed for PMSM motors as well. And I actually got some PMSM motors here, which I got from a company here in Stockholm. These ones are really cool. One of them has encoder, and the other one is just Hall sensors. So it's going to be a lot of fun to start looking at these motors and connecting them to my motor controller. But for now, there is a few other things that need to be done. And one of those things is the current control of the motor. So the way that the simplest way to control a motor is to vary the duty cycle of the PWM wave, but it's not gonna give the best possible control, because if you vary this duty cycle too fast, you will actually hit the current limit, and that will prevent smooth operation of the motor. So what's better to do is to control the current, and by doing so you also control the torque of the motor. And if you can keep the current at the desired level without it overshooting and without it going out of control, then you also get the benefit that if the motor gets stuck, you don't hit the current limit. So for example, if I only control the duty cycle of this actuator, if this actuator gets stuck, then the current will go to the maximum. And hopefully the DRV chip is going to power off the motor, but you never know, because it's better not to hit the current limit. And in any case, there could be situations where if you hit the current limit, the chip will actually latch and would need to be reset manually, and that's undesirable as well. So just to have a look at what current operation looks like, I have plotted some data here, and this is for pitch and yaw motors. Actually, let's add some annotations here, because this is really hard to read. Let's see. So this will be title. Legend will be the first. The first graph is joystick. And the second one is actually we can call it truth. Like it's truth in quotation marks, because this is the velocity truth that I calculate based on the positioning data. So it's not an estimate from the board itself. It's something that I calculate as the post-processing step. But it's not the actual velocity. Like, it's not measured. It's just calculated from the positioning data. And this would be the current. So pitch motor current. This is expressed in amps. And then we have the second one for yaw. This is going to be yaw. And this is currently going to print out the wrong scale on the variables, but I'll have to record some more data to get the correct scale. And this is what it looks like. Alright, so a bit easier to read. So what is going on here is that when the joystick gives the command for the motor to move, actually I'm gonna rewire the joysticks or maybe flip them in software so that it's the same polarity. But when the joystick gives the command, this command is translated into duty cycle on the PWM wave, and the current at first spikes, and this is during the acceleration phase of the motor. And then when the motor reaches constant velocity, then the current goes to the base point, around 500 milliamps here. This is 10 times less because I changed the scale. So this is in reality 500 milliamps. And then when the motor is stopping, the current will go in the opposite direction. This type of spiking is only limited by the slope of the command from the joystick. So there is no. This is just completely open loop control in terms of current. So the current can actually spike as high as the current limit. That would happen, for example, if the motor is stuck. For the yaw motor, it's exactly the same thing. It's just that it's a little bit smoother wave, and it consumes a little bit more current. So this one spikes all the way up to 5 amps. Another thing that's actually interesting to plot is the voltage of the power rail. So remember I said that when the motor is stopping, the voltage is going to increase. And I'm actually going to plot the voltage. Let's see. So I have, because this is running on the control panel, the voltage actually needs to be transmitted over canopen to the control panel before it can be sent to my computer. So I have to just make sure that it is sent over. Let's see. I don't think I've added it yet. So I'll need to actually add it. Let's see, slave. This could be UN16. vmot. This is going to be expressed in millivolts. And slave, I'm going to print it out here. This is going to be my MATLAB scripts that will analyze the data. So actually here in the loader, I'm not going to divide this by 10,000 because this is going to be expressed in milliamps directly. And then that vmot is going to be data field number 10 and divided by 1,000. And then I'm going to add the vmot printout here. And next I'm gonna add the canopen stuff for vmot. So this will actually save your demand, add it here. So case canopen vmot. This is going to go into the manufacturer segment of canopen interface. If you're familiar with canopen, there is different register segments, and basically the manufacturer segment is completely open. Like you can just make it any layout you want, whereas the communication profile specific stuff is defined in the canopen specification. So here I can just add any register. The registers can have any number and any order. So I'm going to read out this. Let's see. This is going to be converted to in16. And then let's see. Self. Slave, and this will actually be locked as well. This will get the data from the canopen packet into the local copy, but I also have to send the data from the slave to the master. So I'm going to add a new section here in the manufacturer segment read, which will do just that. I'm going to add a new definition here, so this would be the register for vmot. This is the register. This is the register number, and this is the index number. So the way that I've written my canopen framework is that I can use 32-bit addresses, where the first byte specifies the address of the node. Then there's 2 bytes for the register address, and the last one is for the subindex of that particular register. And this allows me to have a very generic interface to canopen variables. So I have vmot here. This will be in16. And expressed in millivolts. Now we don't need to constrain it. Let's see. Or actually, I will constrain it. But I'll constrain it as in16. Because this can actually, if there is a bug, this can actually go negative. So this will need to be constrained. this will actually need to be in 32, unless I use 10 millivolt as the scale. So it shouldn't go actually beyond 63 volts. So in this case, it's kind of okay. Just do like this, 63,000. But I think it still may be interesting to be able to measure higher than that. I'm gonna set this. Actually, what I'm gonna do is just let's see. This should work. And if I design something that can run on higher voltages, then I can update that to 32-bit. So next I need to configure the canopen PDO for this variable. The variable is going to be sent at each synchronization frame, which is 1000 synchronizations per second. The master is going to send the synchronization packet, and the slaves, or in this case just one slave, which is the motor drive, will send back all of the variables that have been configured to be sent at every sync cycle. So I need to configure the variable to actually be sent over to the master, and I'm going to do it here. Let's see. Here. So I cannot map any more variables here, so I'll have to create a new PDO. And this will be set like this. Let's see. This is going to be a cyclic PDO sent every sync cycle, and it's going to be sent to the master address, and I'm going to map the variables. There is basically no difference in terms of the mapping on either master or the slave. If there was a difference, then I'd have to configure the new map before setting up the I would have to have different maps for the RX and TX PDOs. But in this case, I can just just modify the map. Let's see, conf map 0 is going to be map entry for vmot. And then I will have, here will be 0, so D2, 0. Putting this one to 0 signifies that it's the end of the list. So vmot will have to be sent separately. And then I'll configure this on master and the slave. So this will go to master. Canopen PDO RX means that I'm configuring the reception side of the PDO, which is going to be on master. And in this case, because I've implemented everything like a registry map, I can just do these operations like write into memory, and it will automatically write to a remote node if the address is different from the address of the current canopen instance, and if it's the same address, then it will write to the local instance. So in this case, if this is running on master, then this will be written to the local address, and if this is running on, actually this will only run on master because it's only the master that can configure the PDOs. And if the address is a slave address, then it will write to the remote registers on the slave. So in this case, I'm configuring that it's going to be sending. It's going to be a transmission PDO, and it will be located at the slave, which would be the motor driver, yeah, and that's it. So this will configure the slave to send the PDO regularly. I'll try to run this. Maybe it works, maybe it doesn't. I don't know. We'll see if it even compiles to begin with. And I'll have to flash the firmware to both the master and the slave. So this has compiled. Now I've flashed the master, and I'm going to flash the slave as well. Power on the board and flash the slave. Now let's see. So I'm going to connect the serial port to the master, and I'll see if I'm getting any readings. This will probably not work because I need to ground connect to this wall. Let's see. Oh, it's actually working. Okay. Let's see here. So this is not transmitting. Vmot is not being transmitted. I'm going to figure out what it is. Let's see. I'm going to connect the serial port to the slave for now, and then I'm going to debug the slave. We have 24 volts on vmot, and let's see if we can get some information about the PDOs. At this point, I think it would be nice to actually add the command line tool for printing out the PDO information. So I'm going to go to my canopen driver, and I'm going to add a new command here. Let's see. Maybe I already have a command line interface initialized here. Let's see. Nope. So I'll need to add the console to device tree, DTS. Canopen console equals console. This will give this will give canopen driver access to the console. And next I will just add this new command. Actually, yeah, just console. Defined by ref. FDT node is the node that's currently being probed on the console, and null if, or actually, no, just like that. And this will be null if the console is not found. And what I can do here now then is if the console is specified in the device tree, then I can add the console command. Console add command. Why? Let's see. There's something wrong. And this can be the same, the command can have the same name as the node in the device tree, so that we can automatically have support for multiple instances of the canopen driver. FDT get the name, FDT node, null, and then we have open. Okay, and then I'll just define the canopen command. Can place it here. And here I want to print all of the locally configured PDOs. So I'm gonna add a subcommand, which will be like the name of the canopen device tree node, and then I could just write PDOs, for example. So if argc, number of arguments, is 2, and the second argument, so argv1, is equal to PDOs, and if this one is 0, which means the strings match, then I will print out all of the PDOs. And now I can use all of the local variables that are local to the driver when I register the command this way, so I don't need to expose that to the rest of the code, which is very practical as a way of encapsulating the device drivers. So I will just find the data structure that contains all of the PDOs. Actually, what I could do, I could find the code that loops through the PDOs. Send pending PDOs, and I can use similar code for printing out the data. So I'll just copy all of this and remove anything that I don't need. So that's a lot of code. Because this will need to loop through both TX PDOs and RX PDOs. Let's see. print that out as a hex number for now. And then we have the code here, just checks if it's a cycle video, so we can just remove that. Let's see. And then I can check if there is anything else I want to print out. Cob ID type, map. Yeah, basically cob ID. That's important. And break if there is a 0 there. Okay, you can flash this. I'm going to include the console interface. This is the pointer that's passed to the add command method for the console. So the console subsystem will store that pointer and then pass it to this command function so that we can retrieve the object that this command belongs to. Okay. Let's see if we can see canopen here. Yeah, canopen. PDOs. So this is the PDOs that we currently have here. U16. And this one. Okay, actually, I should be breaking this loop, so I don't print out the ones that don't have anything. Let's see. I think it is the last bit of the cob ID that determines if the PDO is enabled. So I can check it here. but looking at this map, it looks like the PDO should be sent. So I wonder what is happening here. Maybe I would need to set different index on it or something. Let's see. Let's actually have a look if this is being sent. So I'm just going to add a small print k here. This will be called if the canopen subsystem is actually reading this variable, and then chances are that it's actually being sent to the master. Yep. So we could vary vmot. Actually, it's a little bit harder to vary than this supply. Let's see. The terminal has crashed. Actually, it's not just the terminal that has crashed. It's more than that. Panic. Bug on. Where is this? It's the queue is full. That shouldn't be bug on, actually. Could it be full? Or is it something? Actually, this is okay. If it is 0. Oh, it's actually a stock overflow because you can see it here. And it happens. Interesting. This will need to be debugged. Is there a way for me to get this optimized out variable without having to recompile with optimization off? What I'm going to do is just try to increase the canopen stack. Let's see, canopen C. I'm going to have to find out exactly which task it is. I'm going to try recompiling without any optimization and see if I can get the name of the task. This is very slow. Chrome is stealing all the memory. Okay. Okay. The dispatcher task. I see. That's not surprising. So it wasn't the TX task, it was the dispatcher, of course. Let's see, because dispatcher is actually using much less stack, meaning that if I do a print K out of the dispatcher task, then chances are very high that I will overflow the stack. Let's see. Where is the dispatcher? Yeah, 230, that's way too little. I'm gonna make this 400. And ideally this should be configurable through the device tree. Yeah, now it's working, so no stack overflow. That's good. And I can also change the voltage here. 23 point, let's see, 23.7, 23.3. Yeah, looks good. The sensing seems to work. I'll put it to 24 volts, and now I'm gonna debug why it's not actually getting transferred. Why doesn't it actually appear on the master? That's the next question. So I'm going to enable optimizations again. Okay, great. And let's see, what is this? Interesting. Why is there no console? What did I just do? Oh, I think I need to do like this. I'm just going to rebuild everything with optimizations. Okay. Yeah, works better. So mixing code that's optimized with O3 and code that is not optimized is not a good idea. Apparently something went very wrong there. It actually didn't want to work at all. LED was not blinking, the console was not working. So yeah, compiling with the same compiler flags is kind of important. But I'm not really sure what the problem was. Anyway, the problem is fixed now. Now I'm going to flash the master as well with the latest firmware. Big difference. Ungrounded UART and grounded UART. Okay. Interesting. Are they all inactive? This is wrong because they are active. There is communication going on. Why does this appear to be inactive? I'm going to enable debugging here. Find debug. Oh, maybe because could it be that when I'm writing local stuff, it doesn't actually set the enable bit? Let's see. Because this should be, I think this should be set to enable. Right. Interesting. I have to set the enable bit on the cob ID here, but I'm just trying to figure out if there is anything else I need to do. And also, why does it work on the other one? Not here. Why does it work on the slave side? It's probably that I'm not actually checking whether the enable bit is set. So I'm gonna do like this. Oh, maybe I was completely wrong also about the meaning of that bit. Maybe, right, maybe it's actually signifying whether the cob is disabled. So when the bit is set, maybe the cob is actually disabled. So let's do like this. I see. Check it here. I should have done that from the start. Use the flag. Okay. And disable the debugging here. I'm going to go to main and see everything is actually arriving. So slave. Vmot. This one is probably not being called. So what is going on here? Why is vmot not being delivered? I'm gonna check how I'm actually reading the videos. Maybe I'm kind of misunderstanding some portion of the canopen protocol, where I'm not 100% sure about the numbering of the PDOs, and whether they should be whether they should have different numbers. So let's see here. Have X. Yeah, so actually they probably should have different numbers. At least according to my current implementation. So I'm gonna do like this. I'm going to renumber this PDO. Where is it? 2, 1. I'll set the COB ID to 1. So actually, this is actually wrong, because it doesn't really matter. It has nothing to do with the address. It's more to do with ID code of the PDO. So it's like everybody's going to receive this PDO. I'll do it like this anyway. But it can be a good idea also to include the addresses, because then we know which type of then on the network we can know which node the PDO is coming from. But this is just for debugging. So let's see here. Now I think it should work. This is also an issue that I need to debug. Why can I not flash the card when the motors are powered? Is it only related to a ST-Link, or is there some other issue? Let's see. Now I'm receiving it. Awesome. vmot. So now I can actually plot this. I'm just going to reflash without that message. Did I save the file, by the way? Let's see. I did save the file, but I have to power off the motors before flashing. Okay. Okay. Let's see, FB data. Yeah, cool. And what I'm going to do now is I'm going to exit Picocom, and I will run a script that I have written for gathering data, like run test, for example. And let me just enable the motors. Yep. So now we can run this test, and this will actually save. Let's see. So run test will actually save the test run into the test runs folder and number it appropriately according to current date and time. And then I can have a look at this file afterwards. So I'm going to start this, and I'm going to move the motors. So moving in all directions, and I'm going to stop this. Let's see what data we have. So show data. We'll just call this octave script. But then, yeah, actually this will show. I need to update the script so that it actually picks the files, the latest files from today. But I could edit this 01 check data to load the latest file from today. Let's see. 13/12/36. And just a quick look at the file. I want to make sure that there is nothing wrong with it. Let's see. $42 volts. Wow. Oh, this is going to be fun. Let's have a look at this file. So, show data, and we'll see the effect of stopping the motor. Actually, I have to update this script. I'm going to plot the voltage. So let's create a new subplot, and this will contain the, let's see, this could actually contain pitch bell and yaw bell, and then it will also contain vmot. This would be pitch, yaw, yay, and vmot. Maybe I need to resample this. So the way that I read the data is I always resample the data to the update rate of the internal control loop. Even though I'm printing at 10 millisecond intervals, I need to resample the data to get the interpolated data, which has a constant refresh rate. So that's what I'm doing here, and I need to add a new line here for vmot, so that we get the exact same number of elements as in the time array. now I should be able to plot it. Let's see. On to scale. Is this? This looks a bit wrong. Let's see here. So this is what it looks like. I think there is a problem with I'm reading vmot. So what is the issue here? What is wrong with vmot? Let's see. Oh, of course. I missed some fields here because I have more fields than what I'm processing right now. So actually, it's not field 10, it's more like field 14, I think. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this will be field number 14. And then we can rerun the script. Nice. So this is the kind of spiking of motor voltage that we see when we stop. So for example here I'm stopping, and this is primarily when moving the yaw, because it's a geared motor and it has it consumes a lot of current and it takes time to stop. So when I'm stopping this motor, the voltage rises on the supply rails, and here it rises up to like 40 volts, and on the other spike here it rises even higher, and this is precisely why it's good to have a brake resistor connected to the board, precisely to avoid this kind of crap. Let's see. And this is unloaded motor. So this will need to be fixed. This can be either controlled through software or by connecting the brake resistor. On my automatic brake resistor circuit, it will actually fire whenever the motor supply voltage rises higher than one diode voltage drop between the supply voltage and the current motor voltage. So I need to just get one of those brake resistors so I can test this circuit, and then I should be able to just connect it to the brake resistor output and avoid spikes like this. So next step now is to make sure that the current is controlled and doesn't spike beyond what's necessary. So that will be my next update to this controller. I will pause this video for now and then start over in the next video to start implementing this current controller. And I'm gonna take a break right now, I think.